Hello, everyone, and welcome to our webinar, Inventory Management Using Object and Image Detection. My name is Matt Brown, and I'll be your moderator today. One of my main jobs at SingleStore is to organize our weekly AI webinars. We have 2 per week, and we demo data and AI use cases, new tools, and new technologies during those sessions. I post about these upcoming webinars every week, so if those topics are interesting to you, feel free to connect with me on LinkedIn to stay in the loop with our upcoming AI sessions. I'd also love to hear your feedback or any ideas on topics that you'd love to see in our future sessions. Speaking of future sessions, if you look at the next slide, you'll see that on Monday, we are going to be presenting actions in GPTs, developer tips, tricks, and techniques. You can come join us to see how to integrate GPT actions into your apps. As you probably know, these actions can use AI to execute code. They can browse the web, generate images, interact with voice, connect to APIs to take actions on your behalf, like booking appointments or checking the weather or sending emails. So really cool stuff. It's a fun time to be alive. If this topic sounds interesting to you, go ahead and RSVP right now. There's the link on your screen. I'll put that in the chat in a few minutes. There's also a QR code that you can take a photo of or screenshot of if you want to go that route. Hopefully I will see you on Monday. Back to today's topic, you're welcome to participate in our discussion throughout the session. We have a Zoom Q&A button at the bottom of your console. We have an internal mission statement that we are going to answer 100% of audience questions, even if that means following up with folks afterwards by email. This whole process has gotten much harder as we have thousands of registrants for each webinar now, sometimes hundreds of questions, but we are up to the challenge. So ask away. We will make sure to answer you either today or in an email. Make sure you include your name and email in that question. We will not be answering anonymous questions. If you click to the next slide, you will see that we'd also love for you to try out today's technology. In fact, anyone who tries it today will be entered for a chance to win the latest and greatest new AirPods Pros. All you need to do is visit that link that's on your screen. It's the tiny URL, AI inventory management raffle. I will put that into the chat as well in a few minutes. You may already know that SingleStore has had a free trial for a while, but just in the past 2 weeks, we've announced a new free shared tier. I'll talk about that more in a little bit, but basically you can get access to the core features of SingleStore Cloud without a payment commitment. It's pretty cool. And we'll announce the AirPods winner by the end of today, or by the end of this session, I should say. Let me introduce our speakers today. I think I already mentioned my name is Matt Brown. I'm the head of global growth at SingleStore DB. We have I organize our upcoming webinars. We've got upcoming topics on no-code AI agents, Google Gemini Ultra, which Ayush just told me that we think is releasing either today or tomorrow. So we're going to do a webinar on that very soon. And private RAG chatbots, tons of cool topics on AI. I hope you'll come join those. And then, of course, the real star of our show is Ayush. Ayush is a computer science student at Georgia Tech. I found him online after he created some really cool viral AI demos. We partnered with him on a few projects since then to demonstrate the power of SingleStore DB for AI. Getting started, I'll give a quick overview of SingleStore, why we're talking about this today, and hand it over to Ayush for the demo. Quick, what is SingleStore? Why is it the perfect solution for real-time AI? Well, SingleStore is a distributed relational database system. It can handle both transactions and analytics in the same engine. Years ago, this was great for high power and data intensive applications that critically needed both speed and scale. Some of the examples we like to use are things like fraud detection. So SingleStore has multiple big bank customers. We're not allowed to mention their names due to NDA, but you would know them. Think of the top biggest banks in the world, and you'll be in the ballpark for a couple of the ones that I'm talking about. But anyways, when an end user is at a store or a restaurant and is swiping their credit card, a lot of important things need to happen in milliseconds. There's hundreds of thousands of others that are swiping their cards all around the world. Bank needs to check the account balances, check transaction histories, check typical user behavior, check the location, all of this stuff, and make a split-second decision on whether or not to process the transaction. And it's very important that that decision engine is correct, or you've got a very unhappy customer, or you're out money for fraudulent transactions, or both. So the application really needs speed and scale. The business depends on it. So that was kind of that's been our positioning for many years. But then back in 2017, something else happened, which is one of our financial services customers in particular really pushed us to incorporate vector capabilities into SingleStore. We did that. We have further honed that capability over the past several years. And then the AI boom arrives, which has been awesome for SingleStore. So now we have basically a general purpose database that can handle transactions and analytics and has all of these cool vector and AI functions that people love in their new applications. So high level here, you've got the distributed MySQL compatible architecture. It can handle streaming data ingestion. You see along the left-hand side there, things like Kafka, Spark. You can also see here that we have multi-model capabilities. A lot of people ask, what's the difference between SingleStore and Pinecone or this or that database? We can handle JSON, time series, full text, spatial, vector data. Also, we get a lot of questions about JSON or Mongo. If you like Mongo's simplicity of handling JSON documents, but you don't like the speed or the performance with real-time analytics, SingleStore has an API. It's the SingleStore Kai. It's a API that you can get, I think, 100x faster analytics with no query changes, no code changes. It's very, very cool. Or if you like the power of a data warehouse like Snowflake to handle large-scale BI analytics, but you don't really like the Snowflake prices or slower speeds for that kind of thing, SingleStore has you covered. So all in all, very, very cool. Take it with a grain of salt. I know I'm biased, but I think it's a incredible database for lots of different analytics and transactions and AI. And a lot of what I've talked about today is actually sort of our legacy features. Just in the past few days, we have unveiled a ton of new AI capabilities that you can actually see online if you go to singlestore.com/pro-max, SingleStore Pro Max. You will see that we have announced new features like a approximate nearest neighbors index job service that can automatically execute data workflows or automate your SQL or your Python notebooks. We've got a new database engine with database branching for testing. It's also got smart disaster recovery. And very exciting, we've got that new free shared tier that I mentioned earlier on. You can get the full power of SingleStore's core engine without committing to payments. So too long didn't read. It's a really cool database. We're on the major cloud providers, AWS, GCP, Azure. We're also on-prem. We've got folks that do hybrid for that sort of stuff. So generally, we've got you covered. Ayush, I think I will hand it over to you now. Take it away.
Awesome. Yeah. Thank you, Matt, for that great introduction. And welcome everyone to our inventory management using object and image detection webinar. My name is Ayush Pai, and again, I'm a computer science student from Georgia Tech. And I'm really excited to guide you guys through the fascinating world of AI and its application specifically in modern inventory systems. And definitely, if you have any questions throughout this entire webinar, as we go through the slides and as well as the live demo, put your questions in the chat. We'll try to get them answered during the webinar or at the end. So yeah, let's get started. Just with a basic introduction of what is artificial intelligence, just to introduce the field itself. So If you haven't been living under a rock, you know how AI is kind of transforming today's technology landscape, right? It really represents kind of a pinnacle in machine capabilities, from enabling systems to learn, reason, apply knowledge, and often really surpassing human capabilities in a lot of specific tasks, from machine learning algorithms to natural language processing, computer vision to robotics. AI really encompasses a large range of techniques that are really revolutionizing industries and reshaping our societies. In this session, we'll really explore how AI is specifically altering the field of inventory management itself, and integration of AI with object and image detection technologies. And with also like this type of technology, you can also have like 98% accuracy, with really significant cost reductions. And we'll talk about how we can get this accuracy as high as possible with different machine learning computer vision techniques. And yeah, so let's diving deeper into the realm of AI itself. We focus on computer vision. So this is just a basic introduction to computer vision itself. Really encompasses a large range of tasks, right? Each requiring sophisticated algorithms and deep learning models for these specific tasks. So, image and video recognition kind of form the backbone of this field, allowing machines to really identify, classify, and classify visual content. So, object detection extends this capability, enabling systems to locate and track individual items within an image, which can be really important in the context of a inventory management system. For example, if you're trying to count the number of boxes or stock that you have in a warehouse or a supermarket, you're trying to do this using object detection, and that's where computer vision comes in and where these models come in. So the technical prowess of computer vision is really evident in its wide array of applications. Going a little bit, out of the sphere of, inventory management, you have facial recognition technology, autonomous cars, navigating roads with that, and medical image analysis as well. And in the sphere of inventory management, computer vision object detection really enables real-time tracking and identification of different objects, facilitating a seamless supply chain workflow. And definitely is being used a lot in the supply chain and warehouse industry today, by companies like Amazon Robotics, and other companies that are really automating the warehouse and inventory management process. And it's definitely something that you would want to keep on your radar if you're in this industry, and how it's kind of like revolutionizing how we do inventory management. So just a quick history of computer vision itself, just to give you the understanding of like how we came to this point where we can do this type of crazy technology that we have today. So we kind of began in the 1960s with foundational algorithms for object and shape recognition. And in the 1980s, we had kind of key theories like optical flow, and the start of active vision research. 1990s saw the integration of machine learning, enhancing object recognition and face detection. And 2010s really brought us some deep learning breakthroughs with convolutional neural networks, which are kind of like the pinnacle of today's computer vision technology, which revolutionized image classification, object detection, and semantic segmentation, all of which we'll talk about a little bit later. And each decade really built upon the last, culminating today's advanced computer vision systems that we have. Um, so in the 1960s, we really laid the groundworks for the computer vision's first steps, right? So we had Larry Roberts, I believe a professor at MIT. His thesis really in 1963 kind of introduced the whole field of computer vision with a groundbreaking concept that extracted 3D structures from 2D images, and kind of became a really cornerstone of object detection, and all the way back in the 1960s, right? And this is kind of, very, at the time of there's not many computers, just basic computers, you know, vacuum tube type technology. And he was able to create this type of, thesis that kind of like showed how you could interpret visual information dimensionally, kind of similar to human perception. Following this was the Summer Vision project in 1966, which they were able to construct a system, capable of identifying objects using edge detection. And complementing these theoretical advancements, we really saw significant progress in the field of image processing. And there was many techniques such as the Fourier transforms that were really useful for image analysis that were created in this time period. 1980s kind of really marked a significant advancements in computer vision in the sense of the introduction of optical flow. And this technique really analyzes the movement between image sequences, which is really vital for, processing a video and understanding dynamic scenes. Because images are going to be flowing from, one state to another, and understanding how that works is kind of like the basis of, processing a video. And we also saw a pivotal algorithm, the kind of the groundwork for that called SIFT, which stands for Scale Invariant Feature Transform. And it really it really is an algorithm that kind of improved image matching and recognition techniques and kind of set a benchmark for robustness and object detection in this field. Um, in 1990s, we kind of saw the era of machine learning, and we saw like the Viola Jones face detection algorithm was really famous at the time. It was a really real-time face detection framework, kind of the first one that employed machine learning to revolutionize facial recognition technology. It introduced an innovative approach for feature selection, kind of as you see with these shapes here, that could improve the detection and efficiency speed. So another significant milestone in this period was the introduction of eigenfaces for recognition in 1991. So this method utilized a kind of a PCA, which stands for principal component analysis, which condensed the facial recognition into a manageable computation, kind of doing some type of dimensionality reduction, and used a small representation of images known as eigenfaces. And a lot of linear algebra went into this, enabled systems to really identify faces quickly and with greater accuracy. Finally, one of the biggest accomplishments in this period was the creation of support vector machines, SVMs, which you might have heard of already. And it's still used very prominently today and kind of grew out for, in object detection for image classification. SVMs really provided a powerful method for pattern recognition, particularly really handling like high dimensional spaces, and substantially improving the accuracy and reliability of automated computer vision, visual analysis systems, kind of really laid the groundwork for what we're seeing today in our computer vision applications. And now just to the 2010s and almost to today, we kind of see what this new decade kind of brought in terms of like the most revolutionary monumental progress. 2010s, AlexNet was introduced, 2012 actually, and this actually revolutionized image classifications during the ImageNet Challenge. So the ImageNet Challenge was introduced by people in the computer vision industry to create uh, you know, to create a benchmark that could satisfy a lot of computer vision needs. And AlexNet kind of, was a really, really popular paper, one of the most popular papers of all time that kind of revolutionized everything in this industry. Proved the effectiveness. It could really prove the effectiveness of deep learning and particular deep convolutional neural networks (CNNs), and promoted the widespread adoption of this in the field of computer vision itself. The ImageNet Challenge itself became a pivotal benchmark that kind of spurred a rapid evolution in object detection, classification, segmentation. And in 2015, the introduction of YOLO, which stands for You Only Look Once, really transformed the real-time object detection industry. And this approach really, yeah, kind of unified the traditionally separate tasks of object localization and classification, and enabled the prediction of both aspects in a single forward pass of the network, which is a really big deal. Kind of epitomizing what you only look once means. It's only a single pass through the neural network, and made it much more efficient, improved the speed and efficiency of object detection systems, and really allowed for immediate analysis of visual data. And One of the more new technologies that are kind of developing today is the vision transformer. And this is kind of based on kind of what we see with large language models are based on these transformer architectures, right? In 2020, the VIT, a vision transformer model, kind of applied that transformer architecture to images and was able to leverage, self-attention techniques to focus on relevant image parts. And there are a lot of papers. It's an active field of research today that is kind of breaking this ground with this new technology, and we'll see where it goes. But now we'll go back to some of the inventory management use cases with this computer vision technology. So let's start with automated stock monitoring. So when we think of automated stock monitoring, this represents a pivotal use case in the inventory management sector, right? Really harnessing the power of computer vision can be really useful in this situation. So you can see from these examples, we have this one that says will be over soon based on like how much is left on the shelves. This one on the right kind of shows like the parcel counts of each shipment containers and etc. And this automation can really drastically reduce manual counting errors, significantly enhances accuracy in stock management. Such systems can really identify when items are running low, and even track stock movements, facilitating timely restocking and efficient warehouse operations. And the integration of these technologies really ensures a more robust and responsive supply chain, optimizing overall business operations and really enabling proactive decision making and inventory control. Um, so automated stock monitoring is one of the key use cases that you could use with computer vision. Another one is damage detection and quality control. And these are critical aspects of inventory management where image detection algorithms can really play a crucial role. By integrating these algorithms into the receiving, into the receiving and stocking processes, businesses can really automatically identify damaged goods or quality issues in their products. And this example here kind of shows computer vision being used for, it could detect a seal failure. And obviously this model needed to be trained on, thousands of images of what a seal failure looks like versus what a proper seal is. And then that vision model can identify that. But once you're able to do that, it's super useful for this specific use case. And such automated systems can quickly scan items for defects at a pace and consistency that really far surpasses manual inspections that can be done. And it really greatly reduces the likelihood of defective products reaching the consumer, improving the overall efficiency of the supply chain management system. So another one is efficient warehouse navigation and um, and retrieval, right? And these are really greatly enhanced by integrating object detection with robotic systems. So the integration allows for sophisticated automated picking and placing of items, streamlining warehouse operations, by significantly reducing the time it takes to retrieve items and enhancing the efficiency of order fulfillment processes. So robots already exist in this warehouse uh, place. This whole industry is being revolutionized where robotics with, Amazon Robotics, a lot of these other companies that are automating the whole supply chain process. But computer vision adds another level where it can actually, add another level of organization, speeding up the workflow, minimizing human error, and it really powers these robotic systems that we see today. And the result is a more leaner and more agile operation that can really adapt to the demands of modern logistics and supply chain management, etc. So I see a question in the chat. For many CV applications that you are monitoring, requires industry-specific label data. Are they some techniques you guys have tried using unsupervised or semi-supervised learning? So we'll talk about a little bit of that later in the presentation. But yes, a lot of this does require labeled data, and labeled data is very important to in the supervised learning techniques. And obviously, it's going to be difficult to create large data sets based on specific use cases. There are a lot of general data sets that you could use that we'll get into a little bit later, like just detecting boxes or detecting cans. But if it's a specific use case, specific thing that you want to detect, and a specific object, you would have to create your own data set or figure out some sort of unsupervised technique, which we can go into a little bit later. So now we'll go into a little bit of technology overview on some of the different technology that we could implement to create some sort of inventory management system using computer vision. So OpenCV is a large open computer vision platform, and I'll get into that in a little bit. Um, YOLO object detection is you only look once, mentioned a little bit later. It's the largest object detection software, most accurate currently. And when introduced in 2015, it's continually increased in efficiency and accuracy. We already have YOLO V8, which is introduced by a company called Ultralytics, and we also have image segmentation, and specifically SAM, which is segment anything model. And this was introduced by Meta, and we'll talk a little bit about that. We have multimodal LLMs such as GPT-4 Vision, and we have inventory databases that we can actually store all this information in, retrieve it really quickly. That's what we use SingleStore DB for. So now we'll talk about OpenCV a little bit, just the introduction. So if you haven't heard of it before, so OpenCV or Open Computer Vision Library is a invaluable tool in the field of computer vision, and specifically for the field of inventory management. It really provides a comprehensive set of, programming functions for real-time computer vision, enabling the development of advanced inventory management systems. So with its robust tools for image and video analysis, object detection, and facial recognition, OpenCV can really facilitate the automation of stock monitoring and damage detection, and really can create an efficient warehouse navigation. So it provides all the tools that you need for, color analysis, object detection, and developers and researchers can use this library to rapidly prototype, deploy applications that can improve accuracy of inventory tracking, leading to optimized warehouse operations and streamlined supply chains. YOLO, which stands for You Only Look Once, I already went over a little bit, is a state-of-the-art real-time object detection system that processes images in a single pass, enabling instant analysis. And so versatility, it's really great for applications requiring really immediate detection, from surveillance to autonomous driving, and has continuous evolution with regular updates. So we have surveillance to autonomous driving, and obviously we have a lot of different applications that this dual model could be used for, and this will be using specifically for um, our demo today. So image segmentation is kind of a newer technique that is even more advanced than just simple object detection. So I'll just give you a brief rundown on what the difference is between the two. So object detection is just drawing these bounding boxes around specific images. So we have cars here, but image segmentation is taking this a step forward by actually creating the entire outline of a specific object, which can give a lot more details on and accuracy in terms of the positioning and shape of the object itself. So image segmentation has been around for a while, but SAM, which stands for segmented now, is a model by Meta that was released that can do advanced image segmentation techniques, and can do accurately segment various objects in an image with minimal input, and really leverages deep learning um, for precise optimizations. And this is a very adaptive and versatile technique, and it's able to adapt to diverse sets of images because the SAM model was trained on millions of images. That's why hence segment anything now can pretty much segment anything. And I'm sure there's tuning techniques as well that you can do to make it even better. So another thing is multimodal LLMs, which are kind of new in the sphere of computer vision itself, right? So computer vision has always been about creating these large models with supervised data that can really create these outputs for object detection, facial recognition. But this new sphere of multimodal LLMs can really integrate text and images, sometimes audio data as well, and really understand and generate content across multiple formats. So really excels in tasks requiring, cross-modal understanding like image captioning, OCR, visual question answering, can do pretty good object detection. And it really pushes the boundaries of AI, and I'm really excited to see what we see from, GPT-4 Vision. We have Gemini Ultra, all these different models that integrating these different techniques directly into our technologies here. So now we're going to, start our demo of training a supermarket empty shelf detector. So one question I see here before we get into that is, could the expiration date be tracked in some way with image detection, or is there a complementary technology that can be used in these cases? So if we have like a label on an image, for example, that could uh, display, like the date of the expiration date, um, then we could track that using some sort of technology such as OCR, which stands for optical character recognition, which could actually, read the text on the label. But I'm sure there are different ways in doing that with computer vision, obviously, because without computer vision, obviously, because there's a lot of things that go into, like QR codes, barcodes that can, give this information pretty easily to any warehouse. So you could either do that with, those QR code technologies, or it could be some sort of, OCR that reads the expiration date and, sorts it based on that. So yeah, let's get into this little demo here for training a supermarket empty shelf detector. So the goal of this is to, if you see this image on the right of your screen right here, is to look at a shelf in a supermarket, for example, or store, any type of store where there's inventory, and detect where there are empty spots. And this is going to be a process where we're going to use a supervised technique where we're going to be labeling data and getting a data set, labeling data. And that's would be required to make some sort of, object detection algorithm to do this. So for our demonstration, we'll be training a YOLO V8 model that can detect empty shelves in a supermarket setting, which is a task of great value in retail inventory management. And the training process requires a robust data set of supermarket images, wherein like the shelves are annotated with bounding boxes to really highlight empty spaces. So these annotated images kind of serve as a critical data points for the YOLO model, which employs convolutional neural networks to learn from these examples. These bounding boxes in our data sets are the labels that are the model we're using to understand what an empty shelf looks like. During the training, the model it'll really be like kind of adjust its parameters to as it really processes the data set through multiple epochs, and it'll improve its ability to accurately identify and locate shelf spaces with each pass through the neural network. And by the end of the training, the ULV 8 model will be adept at scanning the supermarket's aisle and really pinpointing shelves and that really need the restocking, and really thereby automating the entire inventory checks and kind of enabling the more efficient stock management that we want to see from this technology. And this capability can really significantly reduce the time and labor that typically required for these manual shelf inspections that we see. So for the data set itself, we have to create a data set for empty shelf detector, we would really need to capture thousands of supermarket shelf images and accurately annotate them by drawing bounding boxes around the empty areas, right? As we saw on this previous slide, that's what that would look like. You have to physically draw these bounding boxes around this. And this is a very tedious process, right? You have to take all these images, draw these examples, then obviously once you draw that file, it will use some sort of annotation tool that can, take the X and Y coordinates of that and create that bounding box and feed that into a model, right? Luckily, in our case, we're using an open source data set from RoboFlow. RoboFlow is one of the most popular tools for finding open source computer vision data sets that are also pre-labeled. And in our case, that we found a data set that has over 400 images that are also pre-labeled with all the bounding boxes. It kind of serves as a starting point for this model's training. But it's definitely important to note to ensure robustness and accuracy in production environment, the data set will really need to be expanded significantly by a few orders of magnitude. With a larger and more varied data set really helps improves the model's ability to generalize across different lighting conditions and product types, etc., making it more reliable in real-world applications. So training a YOLO V8 model is a multi-step process that really begins with organizing the data set into training, validation, and test sets. So we have to ensure the model can really learn effectively and be evaluated accurately. That's the point of splitting it into these different data sets. So the next step is to kind of tune the hyperparameters, such as the image size, the number of epochs, and which would kind of really define how many times the entire data set is kind of passed through and forward and backwards through the neural network. And looking at the training graphs, we can interpret some of these key metrics. So these graphs were outputted once I finished the training of the model. So just understanding what these graphs kind of mean. So the GPU utilization at the top, it kind of really shows how much of the GPU capacity is being used, which is a crucial resource for training these models. And box loss and class loss, these loss graphs overall, they kind of show how the model is doing in terms of locating objects, which is the box, and classifying them, which is the class. And a downward trend in these loss graphs is always a good sign. Kind of shows the model improving its accuracy over the time. We have precision and recall graphs, which the precision really is a measure of the accuracy um, of the predictions, and then the recall kind of shows the ability to find all relevant cases in the data set. And the goal of this graph is to kind of balance the high precision, so fewer false positives, with high recall, which is fewer false negatives. And to get on the output of this training, you get a .pt file, which contains the weights of this model, which kind of really encapsulates all the learned features and patterns that the model has extracted from the data set. These weights are what enable the YOLO V8 model to really detect empty shelves in its supermarket, and with high precision and recall, which we're going for, making a really valuable tool in our case. And then obviously we would need something to store the data about all the empty shelves. So SingleStore really serves as a really efficient storage and retrieval system for data obtained from computer vision models like YOLO V8. When applied to the context of managing supermarket inventory, the bounding box data generated by the model can be stored in SingleStore, and in a SingleStore DB in a certain table. And this data can include, the coordinates of the bounding boxes, sorry, which really indicates the location of the empty shelves. And this information is really critical for, the restocking purposes. So for instance, it can be used to guide the robots to refill, identified shelf spaces precisely. The coordinates x1, y1, x2, y2 really dictate the exact area. As you can see on this bottom right corner, this is a SingleStore table right here. And we have a box ID, we have the image ID, and these are just like the x and y coordinates of the bounding box that is created around the area where there is a specific, a missing thing in the shelf, where the shelf is empty. This can, on a strategic level, this data can be used to program a robot to refill a certain position on the shelves based on, the X and Y position of the bounding box, and can be used to really alert managers about specific empty shelves. And on a strategic level, it can analyze data over time and provide valuable insights for making supply chain decisions. It can help identify patterns in stock depletion, informing purchase orders, and optimizing inventory levels to meet consumer demand without overstocking. Really, really overall, increasing the operational efficiency here. Um, just one more thing before we get into the demo. So multimodal LLM inventory management is another way you could do this, and just have like one slide on it here. So OpenAI's GPT-4 Vision is kind of a multimodal large language model that we talked about a little bit earlier that can perform computer vision tasks. In this case, we can prompt it to get an approximate understanding of how much inventory is remaining in a warehouse, for example. So here's kind of the prompt. As you see, I'll show the full prompt a little bit later, but it's kind of, you are an inventory bot. Your only goal is to output a percentage, and the percentage is just how full the current warehouse is, or current shelf on the warehouse is. And you can really get an approximate understanding of how much inventory is remaining in a warehouse using this type of, large language model, which is really simple to implement versus like training your own model, for example. And one thing to note about this is explainability, right? It's difficult with multimodal large language models, because they're kind of boxes in a sense. They're unreliable in some cases, and you don't really know why the outputs are at what they are a lot of the times, especially with some closed source models like GPT-4. But obviously, we'll get better over time, and we'll see how this technology can transform this industry as well. So let's go through a live walkthrough and a code walkthrough and demo, and definitely ask any questions that you have while we go through this. So let me share. Let me share the screen. All right. Okay, so you should have all got access to this GitHub here that Matt just sent in the chat. This GitHub will give you access to the assets that were used in this notebook, and you will additionally have access to the notebook itself, which will go through all the steps of training the model and then integrating with SingleStore using GPT-4 Vision. So let's go through this right here. So obviously, we first thing we do is our setup with NVIDIA, and we just ensure that we're using a GPU. Obviously, when we're training a model, we want to use a GPU, so you would probably want to go up here. If you've ever used Colab before, you would go to runtime and you would say change runtime type. If you have the Pro version, you could use like A100s, but right now we're just using T4 GPU. That will be really great for training this model. So you just run this right here, and you're just going to confirmation about CUDA and everything. That's everything set up. And so now we have the environment set up in library import. So in this section, we kind of really just setting up our libraries here. Obviously, we're just importing OS, installing Ultralytics, which is the package that allows us to use YOLO V8, and just setting up some other libraries. Just simple stuff here. Run through these cells pretty quickly. So now we'll get to the stage where we train the YOLO model itself. And the YOLO model itself is just a one-line thing to train. It's very simple. And what you do is you want to have a specific pre-trained model here. And the pre-trained weights is based on the millions and millions of parameters that have gone to creating this pre-trained model that has already been trained with millions and millions of images. And basically what we'll be doing here is going to be fine-tuning this model towards our specific data set. Our specific data set is right here. And I'll actually leave a link in the GitHub. I haven't done that yet. I'll do that after this presentation. I'll link to this data set so you guys can actually download it. It's small. It's like 50 megabytes or so. But it's from RoboFlow themselves. You can also explore your own data sets as well. But this data set is stored in my Google Drive, so I put that as the path to that. And here's some of the height parameters that you can also put in. So number of epochs, we're doing 25 epochs, which is essentially just allowing the data set to learn iteratively and finding the best model as it goes through each of these runs. The image size is 640, which is just 640 by 640 pixel images. Particularly on these types of computer vision models, you want to put in square images, and you specify the task, which is to detect, and you could also do segment, which is the different scenario. You have mode, which is train. You could do train, predict, and there's many different modes as well you can explore. This is the pre-trained model, which is YOLO V8S, which stands for small. And small is like kind of like the smaller version. You also have one smaller is nano, and you can go to a really big model, but it takes longer to train. It's a bigger file, etc. You need more powerful GPUs to run that. Specify the data, and yeah, that's pretty much that. So you would click on this, and this would go through the process of, training the data, training the model. So yeah, just going through that. And we also, one thing to note is important, we have our different data sets. So if I go into my drive really quickly, you can see in our supermarket data set, we have our test, train, and validation sets. And these are spread pretty evenly with their images and labels. Or labels are just these files right here that kind of specify the bounding boxes on a specific image, and then they're associated with their images as well. And so what we can see is happening here is it's going through each epoch, specifying the loss, and basically it's going through each epoch and finding the best model that's being outputted. And from that, we can see that. So I already have the model trained. This would take a little bit more time, but I already have the model trained, luckily. So we can see that in action. So let me just stop this training process, and you can run this as well on your end. Um, yeah, okay. So yeah, let me actually connect back to the runtime that we need for the GPU. Um, Change runtime type, save. Okay. So yeah, so I already have the model. Let me just refresh here so you can see the model. Connect with GPU. Okay, cool. I'm just gonna let it run. For some reason, I don't have the model anymore. It'll take like a couple minutes here. Yes, I will send the link for the data set. I'll actually put it directly into the GitHub here. But yeah, just running through these next parts here as we kind of, or actually, I don't know. For some reason, my environment got reset it. So I'm just gonna run through these commands again. So setting up the OS, setting up all the installs. Um, yeah. Definitely, yeah, and this might take a little bit time to just get reset here. So definitely ask any questions in the chat and I'll go through these as this model trains again. Um, or I can just go through the rest of the code as well. Okay. Yeah. So I can send a link to this Google Colab page. This page has my specific like API keys and everything, but you'll have access to this IPYNB file, and you should have access to that in the GitHub that was sent out. Um, so yeah, the model is training again. It will take a couple minutes to here, go through each epoch, but I can go through the rest of the code here. Yes, I can actually demo the multimodal LLM solution. That's a good point. So if we go down here, we have our OpenAI integration where we can see our specific prompt for the system here is you're an inventory management bot. Your only goal is to output a percentage. This percentage is the amount of inventory left based on the input image. And our input image is right here based on our content from the user. And I can just show you what this image looks like from our end. So it's just a warehouse with a bunch of shipping containers, boxes, and we're going to ask, all we're asking for GPT is kind of like a percentage. And so let's just run through this. Actually, I might need to finish training the model before we can run through this. Let's see how many epochs are done here. Um, ooh, for some reason, okay. Okay, that's fine. Um, this is fine. Yeah, so it's just running through these epochs. Obviously, you can run through this whole notebook yourself. It might take a little bit of time to train the model. But I can just explain the rest of the code here and our integration with SingleStore as well. So we have this code right here, which is actually training our model based on these custom. Actually, once we train the model based on these custom weights, we can see that we can actually get the results from this, and these can give the exact predictions of the bounding boxes. Here we'll actually print out the bounding boxes into an array. And it actually gives it into a PyTorch. If you ever use PyTorch, it gives a PyTorch tensor format. Um, and yeah, actually I can't run on the A100 because I don't have access to, the premium collab feature, but that's okay. Um, from this, you can print out the bounding boxes, and these bounding boxes are super important, and I hope I can show that once this runs. Okay. Okay, I think it might be okay. It might be running now. Okay, this is good. Okay, so yeah, this will print out the bounding boxes, and obviously, we can actually what we want to do with these bounding boxes is we want to actually put these bounding boxes and store them somewhere that we could, transmit that to like a robot or transmit that to like a manager who can understand where the specific empty spots on our supermarket is. So it integrate directly with SingleStore. So first thing you want to do is install the SingleStore library. Then you want to connect to the SingleStore database with our connection. So you would put in your specific database here, your name, the specific database, and we're doing this on AWS currently, and the database name here. Then write some simple SQL code here to create our table if it does not already exist. So we have our tables counting is called bounding boxes. We have our x1, x1, y1, x2, y2, and we're putting that directly into our database here. And we create the database, and we take our statement here, and this is kind of the format that we're putting it into. And we connect to the database using s2.connect. We have connection parameters listed here. And for so we have the boxes that were printed earlier. For those, we do a loop through that, the for loop, and we put them all into our SingleStore database. As we can see here, we have our bounding boxes here, and this is kind of like the format for the columns, and we have the sample data here. And this kind of shows like for this specific image ID, we have these bounding boxes around this, and we can see the X and Y positions for all this. And yeah, so let's see the progress on this model. For some reason, it's still not loading. Okay, that's fine. Yeah, so if we definitely if we have enough time for this model to train, I was hoping for this one we could do like a live like model training session to just go through the whole thing because it usually doesn't take this long with the T4. But that's okay. You guys can run that directly in in your Colab environment, or you have access directly to the GitHub now. And definitely, if you have any questions, you can reach out. But yeah, we can go to questions as this model trains, and hopefully we can see an output pretty soon.
Awesome. Hey, Ayush, I might be frozen. Can you hear me now?
Yeah, I can hear you.
Good stuff. Sorry, my Zoom froze for a minute, but I'm wondering if you're ready to start Q&A now.
Yeah, I think we're ready.
Okay, awesome. By the way, I see a note here from Rahul saying you're disconnected from GPU and Colab. Um,
Yeah, for some reason, okay, I think it just got connected now. I got connected, so let's see if it works one more time. But yeah,
okay,
I'll just run through this and we can go through questions as well.
sounds good. I know one question that we're seeing here, and there's been a couple questions about storage, but this one is from Ashish. How is this image data getting stored in SingleStore DB in the form of vectors? And then how are we retrieving these vectors when we're required to train the model?
Yeah. So this image data, so for this specific model, for this specific demo, we're not storing the image data themselves. We're actually storing the bounding boxes that are returned from after we run the model on an image, right? So we train our model, then we run the model on a specific image, and we get the bounding boxes from that image, that can represent the spots where there are empty places in a specific shelf in a warehouse or a supermarket. And once you see that, you take that information about that bounding box, you store as like an array or vector. You put that directly into SingleStore, and then you can retrieve this pretty easily by calling using some sort of SQL to call this data, and you could use it for whatever format you would need if you're trying to figure out like how many bounding boxes there are. This kind of represents, there's one, two, three, four, five, six bounding boxes, which kind of represents there's six empty spots in a specific shelf. And it kind of shows if you're doing some sort of supply chain management, there's six, there's six different spots, which means if there's 6 out of like 20 that are empty, kind of shows like the demand in this specific section is more than another section. And you can do some comparisons like that, directly pulling that data from SingleStore, which can be really useful for a lot of cases here.
Good stuff. And I'm guessing, just based on your previous webinars I use, and also, watching like Akmal's previous webinars and whatnot, it seems to me like there's some flexibility. There's multiple ways to skin a cat, it seems like. And it seems like I've seen different folks use different LLMs to do their vectors. And, we've done stuff on OpenAI and Llama and whatever, and there's some issues in terms of they're not all agnostic, like some vectors don't work with others. But it seems like you can use multiple ways to get those vectors. You can store those vectors in SingleStore, um, and also the metadata associated with all of that. So this is just a really long-winded way of me saying, like, this is how you did it today, but there's lots of different ways to handle this type of problem, right?
Hmm. Definitely, yeah.
Good stuff. I'm seeing let's see. Okay, here's one question. Curious about the deployments that have been done for this. Is this edge deployment? And so if I'm interpreting this question correctly, I just want to point out this is just like proof of concept sort of demo today. This is not like a production demo or anything like that. I also want to point out here is we do have sort of like inventory, and we have grocery store and manufacturing customers. I don't know which ones I'm allowed to say publicly. We have lots of NDAs in place, so I'm just going to go ahead and put this SingleStore customers link in the chat, so you can. These are the ones that were like legally approved to talk about, and so feel free to take a look at that. We've got lots of customers doing some really cool use cases. If you're interested in like seeing this firsthand or asking more questions about your specific company or your specific industry or whatever, we can generally share more information on a phone call. I'm just going to put my email in the chat. Feel free to email me, and we'll set you up with whatever representative handles your industry or your territory. We're a global company now, so we have different reps for the different regions. All right, are there any sorry, go ahead. Were you going to say something?
Yeah, I figured out what the issue was. So with Google Colab, there's limits if you don't have the Pro version. So I had some GPU limits, but luckily I was able to download the model earlier and get like a backup of it. And so I think we should be able to test it with this. So
Cool.
actually, let me just get the imports in. So everything installed. And yeah, there's definitely some issues with Colab if you don't have the Pro version. Hopefully in the future I might get that. So, but yeah, I was just running this a lot earlier today, getting everything, tested and everything. So, um, specifically for Colab, they have like GPU limits on how much you could use. And obviously training on a CPU is less than ideal in a lot of cases. Um, but let's see if this works now. Okay. Okay, yeah, let me just change this path. Okay, cool. So yeah, now it was able to generate results. So here is our initial input, which is kind of like a shelf of, just Coca-Cola, different sodas here. And the results is kind of drawing the bounding boxes around the areas where can we kind of see like where that's empty. And obviously it doesn't do like amazing job because we don't have like insanely big data set, but it did a decent job of identifying like this is a pretty empty spot right here. This spot right here is empty. These different spots are empty. And we can integrate this directly with SingleStore and store these results by, first thing we do is like print out the bounding boxes. Okay, let me just change the path again. This best.pt, if you're wondering, is the best model it was able to create once it ran through 25 epochs. The best model is like the one with the best accuracy, recall, and everything like that. So once we get this, we get our printed bounding boxes. So 210, 33. It's the X and Y positions of the boxes, which are really important for identifying, the positioning on the image where the specific spots are empty. You can integrate that directly with SingleStore. So you would download the SingleStore library, then you establish a connection to your specific database. You would use the SQL, and we already kind of show the process. Then we show, this is stored in here as 210, the X and Y position. X1, Y2 represents the top of the box. X2, Y2 represents the bottom of the box, and we have all the positions of where exactly on the image there are empty spots. So yeah, hopefully, I mean, I know that was a bit of a delayed demo there, but hopefully you get the overall idea, and this could be used for many different images to identify the locations of different missing spots.
Good stuff. Thanks, Ayush. I see we are at the top of the hour, so I'm going to go ahead. Let's get the AirPods announcement out of the way, but feel free to keep your questions coming. Like I said, we are going to email respond to everyone, 100% of the questions that come in, even if we can't right now. First, before I announce that AirPods winner, as I mentioned during the intro, on Monday, we're going to be presenting actions in GPTs, the developer tips, tricks, and techniques. We hope that you will join us. Ayush is going to be presenting that on Monday. And so you can see how to get GPT actions into your applications. Hope to see you there on Monday. I just put the RSVP link in the chat. The announcement you've been waiting for, today's AirPods winner goes to Anna Roy, the head of analytics at Kmart, Australia. I can see why you're interested in this topic. I didn't know Kmart was in Australia. I assume that's the same Kmart we have here in the United States. Thank you for joining. Congrats, Anna. If that's not you, don't give up. We're going to announce one more AirPods winner by the end of the day for anyone eligible who has tried out today's demo. We put that GitHub into the chat. We will also include that GitHub in the follow-up email that has the webinar recording, the recording of this video recording of this session. Thanks, Ayush, for an awesome presentation and demo as always. And thank you to our audience for joining us. Bye, everyone. Have a great day.
Thank you, everyone.